AI-enabled applications on powerful cloud servers provide significant benefits, but offloading personal data raises privacy concerns. Splitting AI or ML models between the end user and the cloud ensures users can leverage cloud computing while protecting their privacy. Dynamic wireless channels due to mobility, jamming, interferences require careful decisions on splitting AI model to balance multiple factors. Trade-offs involve privacy protection, available transmission throughput, and device energy consumption. Dynamic real-time optimization is required in view of the changing radio conditions in real-world deployments. Here's the topology of our system, consisting of 4 main components. UE, running the heads of the ML model and displaying real-time results via a GUI. 5G base station, powered by NVIDIA Aerial 5G with an AI-based spectrum sensing system. AI-based application function, AF, and 5G core, responsible for selecting the optimal ML partitioning point. GPU server, hosting the remaining tail of the ML model. Together, these components adaptively partition deep ML models for image processing, using estimated 5G throughput under various challenging conditions like interference, jammers, and UE mobility. This is the GUI. It runs image processing on input image and outputs classification label and a confidence score. It also displays real-time end-to-end latency. Output data size is the network usage to transmit intermediate data. FPS is processed frames per second. Energy consumption displays UE battery usage. Finally, privacy leakage is measured by distance correlation to quantify sensitive data exposure, with lower values ensuring better preservation. There are fixed splitting and adaptive splitting mode. In adaptive splitting mode, AI-based AF dynamically select the splitting point based on real-time channel conditions. Now, let's dive into the demo. On the left, you'll see the baseline system operating in fixed splitting mode, without the AI-based application function. On the right, the system runs in adaptive splitting mode, dynamically optimizing performance based on real-time channel conditions. In our first scenario, under perfect wireless conditions, both systems perform similarly. The inference results, including FPS, end-to-end delay, and other metrics, remain identical, demonstrating no need for adaptive optimization in ideal conditions. Next, we introduce a jammer into the wireless environment. Observe how the baseline system suffers from lower FPS and increased end-to-end delay, while the adaptive splitting system dynamically adjusts the partitioning point, maintaining better performance. To emulate interference scenario of the edge UE between 2 neighboring cells, we set up the RF cable connect as the shown figure with Keysight UE SIM in pass-through mode. One target UE laptop connect to the NVIDIA Aerial cell in the left, while the laptop on the right runs uplink traffic emulated as the aggressor UE at the cell edge and interferes uplink to the target cell. In scenarios with UE to base station interference or base station to base station interference, the fixed splitting system struggles with similar challenges, reduced FPS and increased delay. The adaptive splitting system, however, adjusts in real time to mitigate these effects, ensuring optimal operation. We also set up another interference scenario between base station and base station due to different time slot configurations. The detailed RF cables and Keysight UE SIM are shown in the picture. Finally, let's deep dive to base station interference environment to focus on the adaptive splitting system's ability to balance privacy leakage, end-to-end delay, and UE energy consumption. By adjusting the optimization weights, the system selects different splitting points, yielding varying impacts on real-time metrics. This flexibility highlights the adaptive splitting system's ability to tailor performance to specific requirements, making it highly versatile in diverse wireless conditions. Through AI-powered spectrum sensing and dynamic AI model partitioning between UE and server, the system enhances privacy preservation and minimizes end-to-end latency with consideration of available throughput. It also helps prolong UE's battery life under varying wireless conditions.